I think the best analogy for an electret is permanent magnet. You have a magnet, and if you have a ferromagnetic material and that comes close to or near the magnet, there's an influence. There's actually work that's being done by the either attraction or repulsion from the magnet. What my colleague Gerhard Sessler and I were able to do was to essentially make an electrical analog of a permanent magnet. With electromagnetism, you can do work. Electric motors and so forth can generate quite a bit of energy. Unfortunately, so far, the electrical analog can only do a very little work, but that little work is important in many respects. In the microphone, condenser microphones existed. In fact, they were invented at Bell Labs by E.C. Wente as a replacement for the carbon microphone. But the condenser microphone required a very large DC bias. A few hundred volts were necessary. And this is because you want an output voltage that's proportional to the change in pressure on the diaphragm, and this large voltage made it pretty impractical from the standpoint of a telephone. Right. So what we were able to do was to replace that battery with a very thin piece of polymer, which we had properly treated to embed charges in that polymer so that they couldn't escape. And so it's the field that's generated from the electret that replaces the need for the battery, which reduces the complication of the electret of the condenser microphone and made it useful in telecommunications. You've got one on that thing. They're basically 95 to 98% of all microphones made in the world today are based on the principles that Sessler and I taught. So it's taken over everything, including outer space. I've made life a little bit easier and a little bit better for a whole lot of people. Is really gratification that is hard to put in words. The lifespan of technology is very short these days. When's the last time you bought a CD, right? Versus 10 years ago.
Yeah.
CDs are still around, but electret microphone, the first commercial electret microphone was in 1968, and it's still the preferred microphone. At some point, it's going to be replaced. And so one of my projects here is to see if I can't come up with a replacement for the electret microphone. And one of my graduate students, Danielle Farrar, is heading that project. And what we're trying to do is piezoelectricity is again a very interesting phenomenon. And most people are familiar with it if you have a gas stove and you turn it on, you hear something go click, 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 and then poof, and suddenly you get a flame. Well, what's happening is that there's a hammer that's tapping on a piece of piezoelectric material, and it taps on it until it generates a spark, right? This is how much energy these things can electrical energy, these things can produce. That's well and good. So there's a lot of energy there, but it's not compatible with many things that we want to do. And so what Danielle is doing is trying to synthesize new materials, to take a material that has a large dipole moment, usually very, very small, not quite in the nano region, but approaching that, and now embed this in this dipole in another material that we can control the mechanical properties of, right? And so if we can do that, then it would be possible to to make a much better and even potentially less expensive microphone than the current Electret.